I think we are recording. All right, great. Okay, so we skipped last week because of the holiday. So this week we're back on a Legion session. So the topic for today that I want to talk about are talking about what actually a context is, and also a little bit more about tasks, and then how scheduling happens. So that you can actually see, like some more details about those various different things. So if you remember the last time we went over, the operation pipeline and stuff, and today we're going to talk a little more about how tasks and stuff work. So the other part of what we looked at the last time in the Legion API, like when we looked at, when you launched a task, you passed in this, if you look at the Legion API, right? If we look at execute task, right, we passed in this mysterious context handle here, which to the user is pretty much an opaque thing. Users get a context when they start a task, and then they have to pass it in whenever they want to tell the runtime to do stuff. And effectively, the context is, it's almost superfluous now that we actually ask users to pass this through. We actually have a, sort of a task local variable inside of Legion now that will actually know that you're in which context you're in. So, at some point in the future, we might change this API to not have to make users pass in context everywhere. But for the moment, we still ask them in a very functional programming kind of style to pass it through. But to the user, it's just an opaque thing. They get a handle, they pass it through whenever they want to do something inside of a parent task, right? And so, but what I want to look at today is what actually happens with this context inside of when you actually do an operation, what this context actually represents, the various different kinds of contexts and stuff like that. Okay, so if we actually go look at execute tasks, is not the best one because I haven't actually dispatched to it yet, but let's see. So for in Legion, let's see if what is it? Issue copy. No, I haven't done that one either. But here I've done for like attach and detach. You can see a lot of things actually now like just dispatch onto this context. So as I said, for users, it looks like an opaque thing, but really what it is, it's a pointer. And you can actually see that in Legion types up here. Oh, this is going to be a hard type def to find. Nope. I might need to find this later because actually finding this type def is actually challenging because a lot of the words, the names are actually overloaded. But that context is just a type def onto actually it might be, let's see. There's the forward declaration. There it is. Right, so this is a type def, effectively gives the user the opaque handle of a context. But really what it is, it's a type def from, an internal pointer to an internal context. So we're giving the user a pointer, but they don't actually see it as a pointer, they just see it as an opaque handle. But internally, it's just a pointer to the reference of, the parent task that is executing, the particular task that's launching, subtasks and so forth. So I'll show you a picture since some of you guys have requested pictures of what's actually happening here. Let's see. So I want to show this picture here. So what you realize is that for every point task that actually executes, or I should actually say single task. So for every single task, which is either an individual task or a point task, and we'll talk about that in a minute, that executes, you always have a context associated with it, right? So every individual task has some kind of context with it. Every point task has some kind of context associated with it. The only orphan context is the top level context, which is a special case that sort of roots our tree of like when you start a new top level task, it has to have a context, and so you have a special top level context, right? But then every point task, whether it's every single task, whether it's an individual task or a point task, right, will have a context associated with it, and that's going to manage all the resources associated with the state of executing this task and any sub operations or subtasks that it might launch. So coming back to Legion, what you actually see is we have a whole file devoted to the context. So we have a header file, right? And the base class of this This type tree is just called a task context, which is the thing that, which is the kind of pointer that we gave back to the user, right, as the opaque handle. There's a whole bunch of things in here and a bunch of virtual methods and stuff that this thing does. It's not a pure virtual class. There actually are some, you can see lots and lots of pure virtual methods here, defining all the things that contexts need to do. But there's also some non-virtual functions in here. So there is some common base, implementations associated with a task context that are the same regardless of whether you're going to be able to launch subtasks or not. If I actually show you the type hierarchy for contexts, let's look at this one. So this is the task context, which is sort of the base type for all contexts. There's two subtypes. There's the inner context variant, or inner context subtype, which is effectively the kind that allows you to launch off subtasks and other kinds of operations below. And then there's also the leaf context, which is effectively a special optimization that, clients can tell us, like, this task, I promise this task is not going to launch off any subtasks or any other sub operations internally. And therefore you can optimize away a bunch of stuff that, a bunch of resources and data and stuff associated with the context that you're not going to need, because we promise you you're going to, or we're not going to do those things, right? And so if the user tells us their task is a leaf task, we can make a leaf context to be associated with that, particular task. And then, under inner context, there's a couple of variants associated with that. There's the top level context, which is a special case, sort of the context with no parent task, which is rooting the tree. We'll talk a little bit about remote contexts, and we won't talk about replicated context today. That's for control application, but they're all sort of subtypes of this inner context class. And so coming back to Legion, in this file, you'll find all the different, flavors of, inner context, which inherits from task context, and leaf context, which inherits from task context, and then you can get like a remote context, which inherits from inner context, and so forth. And so that's sort of the type hierarchy that exists inside of this space. Now, when you actually launch like an operation, one of the most important things that it actually does is it actually records itself with a particular parent context that's executing in. So if we, just showing you something from, let's actually jump in here to, let's see, do I want to go to Legion context? I think so. When you actually, right, so one of the first things that you do when you launch a task or another kind of operation is you actually tell the parent context, hey, I've got a new child operation that I'm kicking off. And this is actually something that, will be done, for every single operation that's recorded in this parent context, so that this context can actually track, all the outstanding child operations, whether they're tasks or other things like copies or inline mappings or attaches or detaches. Pretty much any kind of operation that goes to the operation pipeline always records itself with its enclosing parent context, for the thing that launched it. And we'll track all sorts of things like, how many outstanding children we have and so forth. And this is also where we enforce, things like our, the maximum number of outstanding children that you can have in flight, from a particular parent task and stuff. And so if you exceed some limits, right, we'll actually tell you to block that parent task and stop it from running too far ahead, right? So that way you don't unroll your whole program and have like millions and millions of operations outstanding. For default, like this window is always like 1024. So there's always like, for most applications, like 1024 subtasks or other operations is the most that you can have outstanding inside of a parent task context before you actually block that parent task context and start it. That's this window wait operation here. So anyway, this is always what happens, for every operation that gets launched off, it always records itself with its parent task. And you can actually see this if we go look at legionops.h. This is something that you always, this is one of the most like commonly accessed members of any operation is the parent context, right? And you can see this is an inner context, right? Because you can't have a child operation inside of a leaf context. So that this type is actually more tightly bound. It's actually can be an inner context and not just a basic task context, right? And this parent context, you'll see it referred to all over, all the operations constantly getting or doing stuff or asking the context about, do I have privileges on this region requirement or what have you? And so, and this is just for reference. I should have shown you. this is inside the base operation class. So we are in lots of stuff here, but we are inside the operation class, which was the the operation that we looked at. We looked at like this base class last time, showing all the kinds of operations and how they all inherited from this base operation class to go through the pipeline. So they all have a reference to their enclosing parent context from the parent task that launched them. And so you'll refer to that constantly. Let's see. So one thing that happens if we actually go look at, come back here to Legion context.cc, in addition to registering registering new child operations, this parent context also gets told, every time that an operation moves to a different stage of the pipeline. So let's see if I can remember the name of the method. No, it's not the one that I want. Let's see. What is it called? I'm trying to remember the different stages of what we call these methods. I might have to go look in Legion context.h to find it. Is that the right one? Yes. These are the methods. These sets of methods right here are the ones that I'm looking for. But effectively, like as operations move through the pipeline, they actually will tell their parent task that their state has changed, right? As they complete certain phases of the pipeline. And that actually allows the context to know things like, how many operations do I have that are mapped or have executed or completed, right? Such that, both you can manage that like window weight thing that I talked to you about before, like you can only have so many operations in flight for each parent context. But you can also do things like interact with scheduling, like for the mappers and stuff like that. So knowing that, you have so many operations in flight that are, that haven't mapped or, that haven't executed yet, right? That's actually interesting to manage, your mapping process and tell your mapper, please continue calling select task to map to make sure that the mapper continues making forward progress and so forth. So we can actually go look at some of those. Let's take a look here. Let's see here. Okay, register child executed. So you can see here's register executing child. This is a child that is about to start executing, right? So it effectively just puts it in this executing children map that we have here. This one is actually the more interesting one, registered child executed, because this one can actually effectively influence the mapping process, right? Because so for those of you that are familiar with the Legion mapping API, and I know not all of you have, but let me let's actually do a quick diversion into the mapping APIs, because this is going to tie into the mapping API and how the mapper sees certain things. So if we look in the Legion mapping API, let's see. So one thing that mappers are allowed to choose, right, is the maximum number of, or the minimum number of tasks to schedule before they get preempted from getting calls to select task to map, right? So, mappers are kind of expected to continue mapping operations up to a certain point, but they can sort of set how far do they want to map into the future, right? And so, how many operations do we want to have outstanding to be mapped before we stop the mapping process, because maybe it consumes resources or what have you, right? By default, we set that to 64. So this actually comes back to, and we'll come back to this here in a minute, but this comes back to this, register child executed. And you can actually see, we're actually starting to look at some of the things like, well, I guess this is actually looking at the window size here, triggering the window weight, but actually I should probably look at register child complete. Is that the right one? Looking for the right bit of code. Nope, I am actually missing the right method here. Where's the one on the mapping? I'm a little bit disorganized today because I'm a P-pop and didn't prepare quite as well as the last few times. Let's see. Okay. Yes, this is what we want. So there's some other methods here in this context class for incrementing the number of outstanding, operation. I should probably rename these. This is actually a pretty terrible name. But effectively, what this is doing is incrementing. Saying a particular operation has gone into the map stage. And in particular, you notice I'm not actually passing the name of the operation here. I should actually probably be passing the name of the operation here, so you could actually like debug this properly and stuff if something went wrong with it. But this context tracks, how many outstanding subtasks and stuff are in the state of being mapped or unmapped, right? Or having executed and so forth. And what we can do is that actually creates, sort of a mechanism by which, we actually track the number. We see, like, do we have as many outstanding, tasks that have mapped as we expect to in our context configuration. This context configuration thing is what actually gets filled in by the mapper in this particular mapper API call, right? So the mapper has said, for this particular parent task, I want to have 64 tasks mapped at all times ahead of where the execution is taking place before I stop doing stuff, right? And that sort of toggles this, if we have enough of those things, that sets the context to being in a state where it's active. Or sorry, if we don't have enough of those things, like we set ourselves in a state where we are active, right? And we have to mark that this context is active, and then continue to call back to mapper to ask it to continue to map things for us, right? But if we actually get enough of our outstanding tasks mapped, right? This will decrement the number of outstanding unmapped tasks, right? Then we actually go into our deactive state, right? And then we can sort of tell the runtime, hey, this context, this parent task, has enough outstanding map tasks. It doesn't need to be invoked at all the time to, keep telling the mapper, please keep mapping ahead, right? And that will actually change the state of like the mapper, not getting calls, to select tasks to map quite as frequently. Or sorry, it won't get any for this context. It might still get calls for other contexts, but it won't get any calls for this particular context. And so these contexts manage state like this, right, for the parent task, right? And so one thing that you'll find as a recurring pattern, throughout the whole Legion architecture is that a lot of the state for, what's actually happening during execution is held inside of these different contexts. Okay.
How does this mapper configuration, how does this interact with the window size? Is that different, related?
It's two different things, right? So the window size is to saying, how many things you have outstanding, right? How many things do you have in flight at a time, right? Whereas this is the active versus inactive stuff that the mapper can configure, right, is just pertaining to the number of mapped operations, whether they're tasks or other stuff, right? So mapping doesn't necessarily. So for example, you could have 1,024 tasks in flight, but only a very tiny number of them mapped. But as long as that tiny number has met the whatever the configuration that the mapper set was, maybe it's like 8 or something, right? Then we'll stop calling select task to map, even though we might still be like might still have a giant window of outstanding operations in flight. Does that make sense? Or
so the different stages in the pipeline are each setting their own limits, essentially.
Yeah, well, and yes, and there's really only two that the mapper kind of concerns itself with, right? Like there's the window size, which is like how many operations can this parent task have in flight at a time, right? And then the second one is the number to map, right? Like how many do I need to have mapped to consider myself mapped far enough into the future, right? And so those are two separate processes. They're related in the sense that like it wouldn't make sense to set min tasks to map larger than the window size because that would never be satisfied, right? You'd never have as many operations. If your window size is less than your like minimum task to schedule, then you'll always be continually mapping into the future as much as possible because you'll never be able to deactivate your context, right? You'll never have enough things in flight to support it. But other than that, like as long as this is less than that one, right, they're pretty much decoupled. So. And for reference, there are other ways of controlling like how far you map into the future, right? There's you can specify frames and use that to control it instead. And that's not the default way of doing things, because that requires sort of application direction to say what a frame of operations are and so forth. We're not going to talk about that today. One thing you can look at is like this hysteresis percentage, which says like, as you fill up this window, right? Or if this window gets full, you've launched like all 1024 operations, right? How many of them have to drain before you start allowing new operations to start? Because it's expensive to restart, a task, sort of, you don't want to sort of restart your parent task that's launching subtasks and then have it like launch one and then preempt itself again right away, right? So like, by default, we wait for 25% of the things in this window to free up, and then we start running the parent task again and launching more things and stuff. But this is all mapper configurable, and it all shows up here like in these state operations for the actual context object itself that's tracking all these different things. Okay, so what I think I want to show you guys is where this activate context goes to, so you can sort of see where that goes. So let's jump over to the runtime. Let's take a look at activate context. That's actually not the right one. We actually want the one on the runtime, right? So when a context becomes active, what that does is it actually iterates over all of the processor managers. Now, we haven't talked about what a processor manager is yet, and so we're going to introduce that concept here, which is, for every realm processor that can potentially run application tasks, we actually have one of these processor manager things. And what it's doing is managing the state of that particular realm processor, and we'll see some examples of that, over the course of these talks. But when you activate a context, what that does is it, tells the runtime, hey, this context needs to be active now. Please tell all the processor managers to activate this particular context. So now we can go look at activate context inside the processor manager, right? And this processor manager, what it's doing is tracking, effectively the list of all the contexts that are active for this particular node that we're sitting on, right? So, so it has a context state data structure here, which is tracked by some unique identifier associated with this particular context. And what it does is, it tracks all the active states, right? Because this processor manager is actually going to know about all the subtasks and other operations that are potentially going to be running on a particular realm processor, right? So, or have been associated with this particular processor. For example, if you launch a subtask, one of the first things you do is you say which processor, it's associated with for the purposes of mapping and stuff like that. And so this processor manager knows the name of all the subtasks and other stuff that, have been, are temporarily associated with the mapper with respect to this particular processor, right? But just because we know about that task doesn't mean we're trying to map it all the time, right? We're only going to map it if its parent context is actually active, right? And so we get this context state. And you'll notice that, if we were the first, if we have any tasks associated with this particular context right now, right, then we're going to put this in this set of active contexts, and then we're going to do something about it. So let's see what that does. Right. So what happens is, and this is actually sort of kind of crucial to Legion's forward progress, but effectively, what it's going to do is it's going to say, like, if we didn't have any active context before, right, and we didn't have any mappers that that had anything to had any that are actually haven't been disabled because we haven't hit the limit yet for this particular context, right? Then we're actually going to launch the scheduling task to actually do to start trying to map those particular tasks, right? But if one of these schedulers has already been kicked off by something else, then we know we're going to get a call back anyway, right, from some realm meta task, to actually do the scheduling later, right? But if not, we have to be the ones to kick that off, right? And this scheduler, you often see like in a Legion profiler, the scheduler task, right? And this is actually like really crucial to the forward progress of Legion, is that you'll get these scheduler tasks, which are going to start the process of mapping tasks, which will actually run things, right? And of course, we record ourselves as one of the active contexts. So if we actually go look at launch scheduler context, I don't want to dig too far into this detail, but effectively, all it does is it dispatches a meta task, which is actually going to run later, which will actually handle this particular callback, and it will actually start the process of mapping tasks, which will then enable them to run and then enable them to execute and then continue the process moving forward. That's actually like the crucial forward progress loop inside of Legion, is the process of like deciding that we have tasks that are ready to map and therefore ready to and once they're mapped, then they're ready to execute and so forth. And then they produce new subtasks which come back into this loop as we saw earlier, right? Once they become ready to map and so forth. So this is all this task right here that we kick off is always you can think of this as like the progress task inside of Legion. It's not obvious that that's what's happening, but this is the main progress loop inside of Legion. Okay. I'm not going to talk about how we actually launch off the meta task here. We'll talk about that at a later date, but I will show you where this callback comes from or comes back to us. So we search for scheduler args. Right. Right. So here we get this. This is actually where the callback comes back to us. We'll get this process schedule request. Right, it tells us which processor, effectively kicked off this forward progress thing, right? And it effectively gets the processor manager that associated with that processor, and then it calls perform scheduling. Okay. Effectively, this is going to do two things. It's going to do a whole bunch of things to map some tasks, which we're going to go look at in a minute. And then it says, do we need to build a continuation to continue doing scheduling processes and stuff like that? Because there's a limit to how many things we want to map in every one of these API calls, right? We don't want to have this thing monopolized like our utility processors and so forth. So, the progress should allow other stuff to run, but it does need to continue being called sometimes in order to continue making forward progress, right? And so sometimes we need to, effectively, hit another continuation to keep making forward progress. Other times, we may not have to. We'll just be done at the end of it. Let's actually go look at this perform mapping operations. Okay, so
what was the action at the end of that task? Or rather, you would stop if you just don't have any more work.
Yes, no more effectively, if you've gotten to a point where you've mapped far enough into the future and you don't have any more, tasks that need to, or any more active contexts or mappers that have unmapped tasks, right? Then you're able to continue, or then you can say I'm done, right? Because something else will have to happen in order to make forward progress, right? But if there's still like active contexts which have tasks that are unmapped, right, then you need to continue, doing the continuation to come back and continue trying to map them, right?
And those would be on another context or something.
Most likely they would still be in this particular processor manager. So you can actually get this callback, like this continuation task could happen for several different processors independently, right? So each processor kind of manages its own forward progress separately, but it can reason locally, right? Because like effectively, there has to be either an active task somewhere else that's going to do stuff and be managed by that processor manager, or and if it gets like shifted around to another processor, that will either, like if the mapper decides to send the task to another processor to map it, right, that will actually wake up the forward progress thing for that other processor manager. Does that make sense, or did I jumble that up too much?
I think so. I guess the point here is that like this perform mapping is not just going to map everything. It's going to map some things and then put itself back on the queue.
That's right. And it may not even map anything, right? Like the mapper we could call select task to map, right? And the mapper decides to do nothing, right? And what happens is we actually will like exit out of this perform mapping call without having done anything. We'll still be in an active state and still have tasks to map, so we'll launch the continuation. It may not run right away, right? Because it actually has, it doesn't have the lowest priority, but it actually has a fairly low priority relative to other background work, right? Which may actually make it possible for other stuff to happen, which frees things up, and then eventually we'll come back around and we'll call select task to map again, right? And I do that because like there was actually like a case very early, there was actually a bug like very early on in Legion where like I actually had that priority set too high. And what happened was like the continuation task would just starve out all other things from making progress. Like if you called select task to map and the mapper didn't do anything, you could actually like get yourself into a starvation loop where nothing would happen, because we just come back around and ask the mapper, "Are you ready to map something yet?" It says no. You go back around. "Are you ready yet?" No. "Are you ready yet?" No. And we just like get stuck in that starvation loop, and the other meta task work couldn't make progress. So we actually set that a pretty low priority, but it is possible that like the mapper actually tells us not to do anything, right? And then we want to abide by that, and then come back around and ask it later to try and do stuff. Okay, does that make some sense? Hopefully.
Yep.
Okay. All right, so, associated with this particular processor, right, can actually be many mappers, right? So you might actually have like many different mappers associated with this task, and they'll all have a different mapper ID, right? So you can only have like one mapper of each kind of each mapper ID, associated with this particular processor, right? But what we're going to do is we're going to go in here and we're going to grab all the current mappers that are effectively that are currently here. And it's been a little while since I've looked at this particular method, so let's see if I can page it back in on the fly. So we're grabbing all of our current mappers and checking and getting their mapper manager, which actually is the object that wraps the user level mapper. We'll definitely going to dig into this at a future date to actually look at these mapper managers. But just think of this as like a wrapper around the mapper object that I get that Legion gets handed by the application. Right, and so for each of these, current mappers that we have associated with this processor, right, effectively we're going to look at their queue of tasks that they have that are ready to map, right, and we're going to check the mapper state, effectively check to see if has the mapper asked us to defer select task to map into a future until a future event is triggered, and so forth. But otherwise, we're going to grab all of their tasks that are ready to map and build up. We're effectively trying to build up, a queue of, the tasks that are ready to map for this particular mapper, right? And so, right, and we have to do this for all the tasks that are ready in this particular mapper, right? And once we've got all those tasks, this is where you actually get your call to select task to map. So for those of you that are familiar with the mapping API, right, there's a call in the mapper API, which, is select task to map, right, which effectively says to the mapper, please, here's all the tasks that you have that are ready to map, which of these would you like to do? Now, currently, we're not actually like, one thing that, we don't do at the moment, which we could conceivably do is, and maybe we should do this, and I can actually, point this out here. You might look at this as a bug. It's not actually a correctness bug, but we're actually grabbing like a full queue of all of the tasks from any context which are ready to map for this particular mapper, even if the context is active or not, right? And so, just having one active context that needs to map a task for this particular mapper right now, we're actually telling the mapper, please, select task to map for all of the tasks, associated with this particular mapper, even if their context is active or not active, right? And we get them back, we actually go and kick them off and so forth and check to see if we've satisfied the number of outstanding state or whether the mapper actually tried to deactivate itself by giving us back an event to wait on and so forth. But if not, we actually will go and kick the operations off. And then at the end, we sort of like, put our tasks that are unmapped back on the queue and decide whether we satisfied any active contexts, right? We effectively, mapped any of their contexts and hit their limit on the maximum number that they've actually needed. And yeah, this is all very tricky. And you actually notice that we're doing some very tricky stuff here with the locks. One thing I will point this out, right? So, one thing that we try not to do ever, because it can be very bad, is to hold any internal runtime locks when we call out to the mapper, right? So when we do this mapper call, where did it go? Where did the select task to map call? Here it is. One thing I tried very hard to do is to avoid holding any internal runtime locks while calling the mapper, because the mapper can take arbitrarily long to do stuff, and it might actually call back into the runtime. So pretty much like you'll notice here, like we take the queue lock here to grab the set of, to look at the mapper states and grab their grab a copy of like their queue of tasks that are ready to map, right? But then we release this lock before we actually do the call to the mapper. So we're not actually holding any locks at the point where we call into the mapper. And like I said, that's a general sort of like good discipline that I try to maintain. Like anytime you try to do a callback anywhere, just make sure that you're never holding any runtime locks, because like I said, that tends to go badly, especially if you've got contention and people's mapper calls take a really long time and stuff like that. So we put guards and stuff like in some of the data structures to make sure that like we know that that we have a copy of the queue out here, we're doing a mapper call and so forth and put it back. And that's why this method is actually pretty complicated, is that there's sort of like a two-phase thing happening to sort of, grab the locks, do something, and then release the locks before we do the mapper call, and then retake the locks afterwards and put things back together. Okay, I'm hand waving a bit, and there's a lot of code here. I don't want to go through it line by line because it's very complicated. But effectively, there are two things that, in order to get a mapper call to select tasks to map, you effectively have to have an active context, which we talked about, and how we have tasks that are, ready to map. And then you also have to have the mapper that's ready to accept the select task to map call by not having, passed in a deferral event, to sort of say, I'm to prevent this mapping going forward. This is, like I said, this is the progress loop in Legion. This perform mapping operations, it kicks stuff off, mappers decide what to do, and then, anytime you have an active context and an active mapper, then you have to do these mapper calls, which then, will allow things to map and continue progressing. And that scheduling task is the forward progress task for Legion. So anytime you find yourself like I said, I would be very careful messing with this logic. It's tricky to get right, but it's been robust and working very well for a number of years. That doesn't mean there aren't bugs. I haven't actually proven that like the forward progress in Legion is like as implemented is completely correct. But as far as I can tell at the moment, like we don't ever hang because like we get into a state where we have an active context or an active mapper and we're not actually making progress. So anytime you're wondering like how forward progress happens in Legion, this is the right place to come to. Okay, I want to come back. I want to unwind the stack a little bit and jump back to actually looking at some of the tasks and how they work with the or how they work with respect to each other. So let me actually show you a picture here, and then we'll show you some code for this. But okay, so let me show you one other type hierarchy, and then we'll look at how an application actually executes inside of Legion. So we've talked a lot about tasks. This is the tree of types inside of a task. So, we looked at the general operation class, and I showed last time, and we saw that there are lots of kinds of operations. All tasks that, inherit from the task op class, which also inherits from the operation class that we looked at before. And then you can have lots of different subtasks or subtypes in here, right? So a single task is sort of going to be a generic kind of task that represents a single execution of a task. A multitask represents a group of tasks, right? And maybe group task would be a better name for this than multitask, but for the moment it's called multitask, right? And this is going to be what represents index-based task launches, and then the corresponding subsets of the space that get the slice tasks that get created by mappers when they decide how to slice up a task, right? And then eventually, slice tasks get refined down to point tasks, right? Whereas an individual task is what gets kicked off, by execute task. And there's also shard tasks, which we're not going to talk about today at all. But the main four that you need to know about are individual, point, index, and slice tasks. Now, when you run a Legion application, right, you have a like when we start a new top-level task, right, the application kicks off a new top-level task. We make a top-level inner context, right, to sort of be the root of this tree, right, and we kick off an individual task. The first thing you do with every single task that gets made is, in order to execute, you have to have a task context associated with that, right? So most of the time, for the top-level task, it's an inner context. Conceptually, you could make this a leaf context, but then you can't launch anything. It's just literally like a sequential program, right? You're not launching off any subtasks or anything like that. So normally the top-level task makes an inner context, right? And then you can start launching off sub-operations, right? So maybe you launch an individual task, and it creates a leaf context, right? Because it's a leaf task. You can also make individual tasks that don't do the leaf task optimization, but then don't do any sub-operations, right? So you can have an inner context that doesn't require you to launch any sub-operations, right? It's just an optimization that you're missing by not making it a leaf context. But you can also launch off other operations, like say we launch off an index task, right? Which the mapper then is going to go ahead and slice into two sub slices that it's going to use for a mapping process, right? Slices can be recursively sliced, right? Just mapping back to the mapper API here, right? There's a slice task mapper call, which effectively allows the mapper to take a an index task and break it up into pieces, right? So you can take like the whole space of all the points in the index-based task launch and break it up into into subparts, right? And then this process can be recursive, so you can get new slices that get passed back into slice tasks to map recursively. And what that means is like you can get slices that further refine themselves into more slices, right? And eventually they get once you actually go to map a slice, that's when you actually enumerate all the point tasks associated with slices, right? Slices can have one point task, or they can have some slices will have multiple point tasks associated with them, right? And then for each of these point tasks, they are also examples of single tasks, right? Which can create leaf contexts or inner contexts, right? And then launch off their own sub operations and so forth. And so you will see this pattern inside of Legion pretty much everywhere, where you always have contexts are always associated with a particular single task that's their parent, right? And then for every one of the operations that get kicked off inside of a context, they all know how to refer back to their particular parent context, right? That represents them. And so that brings us back to this type tree. So you can see how this is being used, right? Like every single task can have a context associated with it, right? Whether it's a leaf context or an inner context, that depends on the variant, the task variant that the mapper chooses, right? And then multitasks are representing your groups of tasks. You can find all of this code. Let's show you where this is. So if we look in Legion task.h, right, you'll find the task op, which is the base task class. It's not pure virtual. There are some common functionality here that's shared in the base task op class. But then you can get the single task class, right, which is effectively the base class for either a point task or an individual task. And you've also got multitask here, which is the base task for slice tasks and index task. And has all the stuff associated with those two things. And then you get the individual, you get individual task and point task. And index and leaf are also, or index and slice are also in here. Okay, so you'll find all the different implementations of these different tasks in here. One interesting thing that occurs here, if I come back to this particular diagram here, is that not all of these operations go through all stages of the pipeline. Some of them appear in the middle, and some of them sort of can skip certain stages. So for example, the individual task that we looked at the last time we talked about Legion goes entirely through the pipeline and it doesn't skip stages, right? However, if you look at like the other kind of task that gets launched from a parent task, which is an index task, right? Like that actually goes through the dependency analysis stage and through the mapping stage, but then it doesn't get past that. Its mapping stage is effectively to be sliced into slice tasks, right? And slice tasks are the things that actually get sliced recursively, and then eventually they decide to be mapped, right? And when they get mapped, what they do is they just enumerate point tasks, right? And then the point tasks are the things that actually do the mapping process and will go through the rest of the pipeline and execute themselves. When they're done executing, they effectively tell their slice task that they have executed, which then tells their parent index task that it's executed. And then when that index task is done executing, it tells its its parent context and stuff like, hey, I finally finished executing, right? And the same thing for commit and completion and committing the tasks as well, right? They all sort of like propagate their, as they move through the pipeline, like the point tasks, they tell their slice tasks, which then, propagate the information back up through the through the hierarchy back to the index task that actually owned it. Individual tasks are like a normal operation. They go all the way through, they do all the stages, they don't skip anything. But index tasks that get refined into slice tasks, which get enumerated into point tasks, right? They actually can skip stages and do some unusual stuff. And they don't all like these things only appear after the dependence analysis stage, right? They only occur once this index task has been sliced by slice tasks by the mapper, right? And so therefore, like they don't actually show up in the dependence analysis stage ever. And so forth. So that's like one thing to be aware of, is that you may find stuff over here, like if we look in Legion task.cc, right? Or I guess really I should be over here, and it should have been an H, but you'll find like if we search for like the trigger dependence analysis stage of the pipeline, we'll find it in the virtual classes. We find it in, there should be individual task here. Yeah, this is an individual task, and we find it. Let's see. Did I lose it? And we find it in the index task, but we don't find it anywhere else, right? I guess technically it is in slice task, but I'm betting that is just a, I think that's an old method that still has the assert false in it. Yep. Yeah. So you see, like, slice tasks should never ever come through this trigger dependence analysis stage. So that's one thing to be aware of, just as you're working your way through some of these operations and realizing, like, why do some of them appear in the middle of the pipeline and not appear at the end, like as they first come through the beginning of the operation. That's because, like, these index tasks and individual tasks are the only two things that can be created by the application, right? Everything else is derived sort of implicitly inside of the runtime, but they're still operations and they still go through stages of the pipeline. It's just that they propagate their information as they change stage up through the hierarchy back to their parent index task. Okay, I've got 10 minutes left. There's one other thing that I want to mention here about these contexts. Since we started off with contexts, we'll finish with them. So one interesting thing about inner contexts, right, is that they can actually exist on multiple different nodes. And the reason for that is that you may end up mapping some of the tasks that get created, inside of this context on a remote node from where their parent task was running, right? So you might like you might launch off an individual subtask and then on node 0, but then it gets mapped on node 1, right? And so you still need to have a way to refer to the context associated with, your parent task, even on a remote node. So one thing that will happen is we actually have a way of representing those contexts that are an inner context but are also on a remote node. So if you actually do have to have that happen, we have this special class over here, which is the remote context. And what this is it's effectively just a copy of the inner context, but represent on a remote node. And in particular, there are some things that have to happen on a remote, like when you actually call into the context to do stuff, right? This remote context actually knows that it's remote, and can actually dispatch the operation back to the owner node for this particular context, to the one where it was originally created, right? And so when you're looking for remote, whenever you encounter a remote context, all that means is you're mapping a task on a node that's remote from where the parent task was actually executing. Right, and there's a whole bunch of virtual methods, and actually there's not too many. It's not a very big task, but there are some virtual methods in here that we actually will propagate, method calls back to the owner node for this particular context. So just letting you know, that's what the remote context is for and how it differs from, other kinds of inner contexts. You can also go look at this top level context, which is sort of like the special case for root stuff, and this has to do with control application. We'll get into that another day. That's a special kind of inner context that knows it's been control applicated and so forth. So I think I hit everything I can do today without digging into a lot more detail and stuff. Are there questions that I can answer before we wrap up for the day? No questions. I can't have explained it that well.
Can you I mean, this is not a very technical question, but what's the relationship between the operation and the context? Like, why is there two different things? They seem to be pretty well aligned. Is that right?
They could be. So one thing that I found, it used to be the case that I suppose there is kind of this one-to-one context, or sorry, one-to-one relationship between a single task and an inner context, right? Uh, or just or between a leaf context and a single task, right? Because you don't ever notice there are no contexts happening off of the slice tasks or the index tasks, right? They always have to be refined down to their point tasks, and then those point tasks are the things that are associated with the context that make context for executing, right? And I actually used a couple like very early on in the Legion architecture. I actually didn't realize that I needed these separate contexts separate from the tasks. Like we actually like stored all the data that's now stored in the context objects directly on the tasks themselves. But effectively you want this decoupling because you don't know whether you want a leaf context or an inner context to be associated with a single task operation. Now, you could conceivably, I guess, like couple the single task class to the task context class, but that those are both like abstract classes, and so like I didn't want to have the cross product of like, do I have an individual leaf context and an individual inner context, and then a point task leaf context and a point task inner context, right? And so I decoupled those two things to make it so that effectively there are these two separate type hierarchies, right? And then you create the one-to-one relationships, between these two things and these guys down here, depending on which one you needed. Just felt a little cleaner to me than trying to couple them together.
Okay.
Yeah.
But in a lot of cases, you have an individual task, you launch an individual task, it makes its own context. That task launches a subtask that makes a subcontext.
That's right. Yeah, and that would be pretty normal, right? Except when you toss in these index tasks, right? That can then slice down to lots and lots of point tasks, right? And so you don't want to try to share any kind of context across them. That would be really, really painful and stuff like that, right? But yeah, I used to couple those two things together, and I teased them apart a number of years ago, but it was at least like 3 or 4 years of Legion before I decided that was necessary. So yeah, I don't mind architectural questions like that at all. That's a good one, because like I said, that was the way things used to be done. So yeah. Okay. Barring any other questions, I realize that was a lot of information today. There's more to look at inside of tasks and contexts and mappers and processor managers and stuff, and we'll continue to do that. But they all kind of get intertwined, and so trying to slice through a part of them is challenging. But the more we encounter them, I think the more they'll make sense. But I do want you guys to have these kinds of pictures in your head of like, this is what sort of the objects that exist as you recursively launch tasks and stuff. What that looks like. So when we encounter these different things, they actually make some sense to you, and you have some understanding of what they are. Okay, next week is a Realm session. So hopefully I'll see you guys all there next week. Okay.
See ya. Thank you.